Hello, this is Thomas Warwick, welcoming you to this Bite-Sized Bio webinar, which today is sponsored by Eppendorf. Eppendorf is a leading life science company that develops and sells systems for use in laboratories worldwide. The product portfolio includes pipettes, pipette tips, centrifuges, mixers, ultra-low temperature equipment, and more. Today's presentation is entitled Endpoint PCR Setup and Optimization, Best Practice, and is being presented by Dr. Stefan Reithmuller from Eppendorf. Dr. Stefan Reithmuller studied technical and applied biology in Bremen and wrote his master's thesis at the Max Planck Institute in Magdeburg. During his PhD at the Institute of Biochemistry in Kiel, he characterized the soluble IL-6R associated with chronic and inflammatory diseases with the help of PCR and other techniques. Before joining Eppendorf, he was a postdoctoral researcher at the Pharmaceutical Institute in Kiel. As always, we will have a question and answer session at the end of the presentation. So please type any questions that you have into the questions box, which appears on the top right panel of your screen, and I'll put them to Stefan at the end. Details of how to access the on-demand recording of this webinar will be sent to you by email shortly. So now, over to you, Stefan, for the presentation.
Thank you, Tom, for this nice introduction. And hello, everyone, to today's webinar. It's my pleasure to talk about endpoint PCR setup and optimization. And with this, let's just start. Today's talk is divided into 3 sections, and the first one will deal with the PCR reaction components. The first thing I would like to address here is the target DNA. So this is the sequence we amplify in our PCR, and this should be kept as short as possible. Why? This would reduce the risk of secondary structures, so your PCR is easier to control. If you want to check your target DNA for secondary structures, you can do this with a tool called Vector Builder. It's a free tool, and I can really recommend it. The same is true if you want to check for RNA. You can use another tool, which is also for free, which is working well. Another advantage is if you have a short target DNA, that you can also shorten the elongation time, and this will shorten your whole PCR. Then we are coming to the template DNA, and here the appropriate template DNA concentration is quite important. So when working with plasmid DNA, we use normally 0.01 to 1 nanogram in a sample of 50 microliters. When working with human genomic DNA, the range is between 3 and 300 nanograms. Too much template DNA can increase the risk of unspecific primer binding, so that's why it's recommended to use these kind of ranges here. Primer, of course, are very important, so a good primer design is essential. It's very important for a robust PCR system and, of course, for the specificity of your PCR. Here, I would recommend to use a final primer concentration ranging from 0.1 to 1 micromolar. If you use more, this could also inhibit the amplification. There are some general rules when talking about the characteristic of primers. So normally primers are between 15 and 30 bases long, and the GC content should be between 40 and 60% as a rule of thumb. At the 3' end, it's recommended to put there 2 Gs or Cs because this improves the binding of the polymerase and thus elongation. But on the other hand, more than 3 Gs or Cs are not recommended because they could lead to non-specific priming. Furthermore, it's important that the primers are not complementary. because then they form primer dimers, and this is, of course, nothing you want to have in your PCR. Then there should be no self-complementary parts in the primers because this would cause self-priming. And also direct repeats like 4 A's in the row can also lead to problems like frame shifts and mismatches. Here I just listed a few tools I could recommend to you, which are all for free. So in case you need to design new primers or set up a new PCR protocol, then first it makes sense to look for your target DNA, which you could find, for instance, on NCBI, and then first check if your target DNA has any chance to build secondary structures. Then you can design your primers. There's a nice free tool which is called Primer 3, where you can put in a lot of information. And then once you have designed your primers, it makes sense to blast them again using NCBI in order to make sure that they really bind where they should. And in the end, you can perform final quality control with a tool called Net Primer. And this also gives you a rating of your primers. And this is also a nice thing I could recommend here. Yeah, the polymerase in magnesium ion concentration is also an important topic. So again, when talking about reaction volume of 50 microliters, we normally have 1 to 2 units of polymerase. This is totally sufficient. In case that you have inhibitors present in your sample, it makes sometimes sense to increase this concentration of DNA polymerase to improve the yield. However, it's also true here, in case that you use higher concentration, this could lead to more unspecific products. So if you don't have any inhibitors in there, it's totally fine to use 1 to 2 units of DNA polymerase per sample. The magnesium ion concentration is also important because magnesium is an important cofactor for the polymerase. In most master mixes, we find magnesium ions as magnesium chloride, and the magnesium ions are in a concentration of 1 to 4 micromolar. And some polymerases, they prefer magnesium sulfate instead of magnesium chloride. Yes, controls are also important. So normally each experiment should contain a negative control and a positive control. And what is also recommended is to use one master mix for all samples. And the order in which you add the components of the master mix are also quite important. So I would recommend to keep the order which is mentioned in your protocol, because, for instance, there are some things you shouldn't do, for instance, to add the water first and then directly the polymerase without buffer, because this would harm the enzyme, but I think this is quite clear that order makes sense here. Okay, some words to the negative control. This is a sample which contain no template, and you add water instead of template DNA. And in case that you have any bands in the gel afterwards, this indicates that you have contamination. And then the only thing you can do is to change all the sources, so all the reagents and solutions, and clean the pipettes. And yeah, that's why it makes sense to always perform a negative control. And to avoid contamination, it makes sense to aliquot the PCR reagent and primer sets into number of tubes and change the tip for every sample, also including the replicates. The positive control is also important because it tells you that everything is fine with your master mix, that your PCR is working well, and that you don't have a high concentration of inhibitors in your sample. So normally the positive control is made with a target DNA proven to work. So a sample you know well, where you know how much signal you get normally, and then you know that everything is ready to go and everything is fine with the master mix. In case that speed is important for you, and if I remember my time during my PhD, speed was important when using the thermocycler because we just had one single thermocycler for the whole institute. And sometimes I had to book the device or time slot for the device 1 or 2 days in advance in order to be able to use the thermocycler. And yeah, it would have been beneficial to use fast PCR master mixes at this time because with these master mixes, you can perform many more runs per day. So this figure just shows how much you can increase the speed of your PCR. So let's say you have a standard PCR protocol with 3 steps. You're using a conventional cycler, a standard cycler, and standard reagents. Then your run maybe takes like 90 minutes, and you can perform round about 5 runs per working day. If you use fast PCR master mixes and the fastest thermal cycler, which is currently on the market, which is the master cycler X50S, you can speed up your PCR massively and reduce the runtime to 16 minutes. This means you could perform 30 runs per day. And if you use a 2-step protocol instead of a 3-step protocol, you can further decrease the runtime to 12 minutes, meaning you could perform up to 40 runs per day. So in case speed is important, this could really help here. So this brings me to the next session. And as I have just talked about fast PCR master mixes, the second thing you need is a vessel which is suitable for fast PCR experiments. And here you have different options. And what is important in general when performing a PCR is the heat transfer from the thermoblock into the reaction into the sample. And this depends on the vessel wall thickness and on the reaction volume. So normally in a fast PCR protocol, you're using 5 to 10 microliters, so rather small volumes because this is beneficial. And most of the fast PCR consumables, they have thinner walls because then the thermal conductivity is improved. And most of these fast PCR consumables are made of polypropylene. And polypropylene has one problem. At a certain point, it cannot get thinner because then the tubes smash easily. And there are some other materials you can use, like polyethylene. This has a much higher thermal conductivity. And the results on the next slide underline that it's sometimes beneficial to use fast PCR tubes or strips made of polyethylene. Here you see the results from 2 fast PCR protocols. And here you see the both protocols which have been used, and you see that the step time is very short. Like for instance, here the denaturation just takes 2 seconds and here just 1 second. So the protocols are very, very short. And here you really see the benefits of polyethylene because the amplification only worked really well when using the tube strips of polyethylene. When using all the other tubes made of polypropylene, you see that you have less or almost no amplification here. So in case your protocol is really short and you really want to save time, then it makes also sense to use this tubes or tube strips made of polyethylene. Another point I would like to address here is the risk of evaporation, and this is a very important point because if you have uneven volume in the wells due to evaporation, your results are incomparable and you have to repeat the experiment. And this, of course, is waste of money and time. So what could we do to avoid evaporation? First of all, the pressure of the cycler lid is very important. The pressure should be reproducible and high in order to avoid evaporation. And normally when working with tubes or strips, you don't have so much problems with evaporation if you have a thermocycler with a well-working lid. What we recommend is to use doom caps because doom caps are better as the cycler lid can put more pressure on the consumable. And what also is important is that there's always a minimum number of tubes per run required. So for Eppendorf cyclers, you need to use at least 5 tubes because if you use less, it can happen that the heated lid will smash the tubes and then your sample is lost. So that's why in the operating manual, you find that you should use at least 5 tubes. And also in the manuals of other manufacturers, cycler, you find that information it's quite important because otherwise you can lose your sample. When working with PCR plates, the best protection from evaporation is to do heat sealing with heat sealing films or foils. And to do that, you need to have a heat sealer. And if you do heat sealing, you're really on the safe side. So you normally should have no problems with evaporation. But sometimes it's beneficial to use self-adhesive films or foils in case that you would like to add a reagent after the run or maybe in between, or you would like to store the sample for some hours and then resume with the next step. So then it makes sense to use self-adhesive films and foils, but they provide less prevention against evaporation. And that's why it's very important that these films and foils are applied well. And what I do in the lab is to use a sealing paddle, also known as plate sealer. I just made a photo of the ones we have in the lab. And this is very helpful to really seal the plate perfectly. You see here every well, and you see also that the edges are well sealed. And this helps you a lot to avoid evaporation. And I really recommend to use these sealing paddles. Okay, what else is important? Of course, the purity of your consumables is very important. So Eppendorf offers different purity grades. And you see that the PCR grades here are free of PCR inhibitors, RNAs, DNAs, and human DNA. And why it's so important that your consumables are free of human DNA is underlined by this short story. So maybe you have heard about the phantom of Fibron, or also known as the woman without face, who was a hypnotized unknown female serial killer since her DNA evidence was found at numerous crime scenes in Austria, France, and Germany. And the only connection between the crimes was the presence of DNA from this single woman. And after many, many years, around about 15 years, the investigators concluded that there was no phantom criminal and that the DNA was present on the cotton swabs, which were used for collecting the DNA samples. And there was a woman who was contaminating these cotton swabs in the factory where the swabs were made. And yeah, just this little story underlines how important it is that the consumables are free of human DNA, and this accounts to the tubes and plates, but also to the tips. In case that you have low DNA concentrations in your samples, or you would like to store your samples for a longer period of time, then it makes sense to work with low byte consumables because they provide an improved recovery rate of DNA and RNA because there's less binding of the molecules to the vessel wall. Furthermore, if you have very complex studies or automated applications, it might be a good choice to use the Eppendorf TwinTech Trace PCR plates. They have a unique laser engraved optical guiding grid, which helps you for quick orientation. Also, when you're pipetting manually, it's a good help. And you can get these plates with customized barcode, and on every plate you have a lot number, laser engraved, as well as the expiration date. And this is also true for the new PCR TwinTech plates bio-based, and they help in case that you would like to reduce your consumer-related carbon footprint in the lab because they are made of bio-based polymer, and they maintain the identical technical performance like the standard TwinTech plates, and there's traceability along the entire supply chain. Pipetting is the next thing I would like to address because it's also quite important. So the first thing which is important is to choose the right pipette. So in case you would like to pipette 100 microliters, it makes totally sense to use the 100 microliter pipette and not the pipette for 1000 microliters. Then it's beneficial to use a small immersion depth while aspirating and to aspirate vertically. A pre-wetting of the tip makes sense, and a slow and uniform piston movement is also very important. And a delay before taking the tip out of the liquid. When dispensing the liquid, the holding angle should be like this or similar, and the liquid should be released slowly against the vessel wall. In case that you have volumes below 10 microliters, you could also release the liquid directly into the sample and then mix gently and spin down the liquids. Yeah, and sometimes it makes sense to work slowly, even though sometimes times matters. So in case you're working with electronic devices, it is recommended to put them to the lowest speed. And in general, it's beneficial to work with electronic pipettes because they could help you to increase reproducibility and increase efficiency. In case that you're working with very viscose liquids, like for instance, you work with a viscose polymerase, which is stored in glycerol, then it makes sense to use positive displacement instruments. And these positive displacements pipettes, they are in direct contact with the liquid, so there's no air fusion. The piston is in direct contact with the sample, and this helps to improve accuracy when working with viscose liquids, foaming liquids, and also hot and cold liquids. And sometimes it's also needed to calibrate the pipettes to do service, and there are some wear out parts like the piston seals, and sometimes it makes sense to replace them to have the best performing pipette. Okay, and this leads me to the last section of today's talk. And the first thing I would address is the ramp rate. So the ramp rate is the change in temperature per second. So for each thermocycler, we have a heating ramp rate and a cooling ramp rate. So to say, the heating speed and the cooling speed. And normally this is not the same. So normally the heating is faster than the cooling. And if you now take a look in the technical data sheets of the manufacturers, you find different terms which are related with the ramp rate. For instance, max ramp rate, average ramp rate, measured ramp rate. And sometimes it's a bit confusing and misleading. And on the next slides, I would like to explain this in detail in order to explain this a bit. So here you see a cycler with linear ramping, meaning that the temperature increase here between those two dashed line is linear. And on the other side, you see a cycler with variable ramping. So here in the beginning, the ramp rate is quite high, and then it's decreasing, and you see that it's not linear, and that it's not good if you want to have reproducible results. So how do you notice that a cycler could have variable ramping? Sometimes cyclers state the max volume, max ramp rate, so the fastest speed, which is the speed here in the beginning, and the average ramp rate. And in case that there's a big difference between max ramp rate and average ramp rate, then this is an indication that you have variable ramping. And sometimes the maximum heating ramp rates, which are stated in the technical data, are misleading because you see here, for instance, that we have measured the total runtime of different cycler models here. So we measured the time once the thermoblock has reached 95 degrees until the time when the thermocycler has reached the hold step. And you see that we have tested different cyclers with really different maximum heating ramp rates. And if you take a look here at the master cycler X40, for instance, it has the lowest ramp rate, heating ramp rate, of 3.3 degrees per second. But it's much faster than some other devices with higher max heating ramp rates. So why is this the case? Because max ramp rate is just one point to consider, and max ramp rate does not say that the ramp rate is linear. And if you have a much lower average ramp rate, then the term is misleading. And there's a second reason why just looking at maximum heating ramp rates is misleading. And I will talk about this after the poll, because we will now have a short poll in between, and I'm happy to receive some answers from your side. So the first question is, for which endpoint PCR applications would you like to have more information from Eppendorf? Standard PCR, cDNA synthesis or RT-PCR, cloning, multiplex PCR, or NGS library preparation? I see that we already have some feedback there, but I will wait a few more seconds just to give everyone the opportunity to answer. Okay, thanks a lot for your feedback. I see that there's a big interest in cDNA synthesis and RT-PCR, which is a very important feedback for us. And we will plan to publish something then in the future in order to provide you more information on this topic. Thanks a lot. And this leads me to the second question of the poll, which is, which volume range do you use most frequently in your PCR cycler or cyclers? 1 to 10 microliter, 11 to 20 microliters, 21 to 50 microliters, 51 to 100 microliters, or 101 to 150 microliters. I see that many of you using rather small volumes, but we will wait a few more seconds. Okay, thanks a lot for your feedback. We see that most of you using volumes between, well, 11 and 50 microliters, but 20% also using 1 to 10 microliters. And this leads me to the next slide of my talk. I said that there's a second reason for the different total runtimes. And the second reason are the overshoots and undershoots. So first of all, what is an overshoot? You see here a temperature profile of the master cycler Nexus. And here you see the denaturation step. So the set temperature is 95 degrees. And in the beginning, you see this small peak here. This is the overshoot. And the overshoot is performed in order to reach the desired temperature in the sample faster. And the overshoot as well as the undershoot are depending on the sample volume you are using. So Eppendorf, for instance, has 4 different temperature control modes. The fast mode for 10 microliters or less, the intermediate mode for 10 to 20 microliters, and standard mode for 20 to 50 microliters, and safe for volumes higher than 50 microliters. And there are other thermal cyclers where you can just put in the sample volume, and it's very important to have a tool in order to that the device adjusts the overshoots and undershoots, because if you don't have such tool, this could also lead to not optimal amplification. And you see here that we have also measured the temperature profile of another device, and this device uses a much higher overshoot, and the overshoot is also longer. So the over and undershoots have different length, and this length also influences the total runtime of the protocol. So this is the second reason why it makes no sense to just focus on maximum heating ramp rates when talking about speed of a cycler. And if you would like to transfer a PCR program from one cycler to the other, the different ramp rates and the different overshoots and undershoots of both devices, they could also lead to problems. Furthermore, it could happen that both devices have different homogeneity and temperature accuracy. And sometimes, if the PCR does not work on the new device, then there's no way out. The PCR protocol has to be re-optimized. And there are some cyclers on the market which offer tools to automatically adjust the ramping rates. So Eppendorf, for instance, offers the program migration feature. There you just put in your desired runtime of your PCR on the new device, and then the ramp rates are adjusted automatically, so you don't need to put them in, and this helps to migrate your program. And this is a tool which is very beneficial. But sometimes when talking about overshoots and undershoots, there is no way out and the protocol has to be re-optimized. The next thing I would like to talk about are the Peltier elements. And the Peltier elements are responsible for heating and cooling, and they sit directly underneath the thermoblock. And here you see a photo of the master cycler X50. And here you have 6 different Peltier elements, and they are all center fixed, indicated here. And center fixing had the advantage that the heating showing here in red is really homogeneous. So you just have less temperature here in the area where the Peltier elements are fixed, but here you don't have any sample in there, so this has no influence on the sample. And there are some other cycler models on the markets with use side fixing of the Peltier elements. So the elements are fixed here at their sides, and this could lead to the fact that you don't have an optimal temperature transfer here, especially at the edges and in the corners. And we have performed an experiment to show this. So if you perform a PCR on the master cycler X50, you see that the temperature homogeneity is quite nice. You see the 2 bands you should like to see. And if you use another cycler, which has side fixing of the Peltier elements, you see that really at the edges, for instance, looking at well H12, you see almost no signal. And yeah, one reason here could be that the Peltier elements are side fixed. Another topic which is important is that it makes totally sense to perform a cycler check once per year. And in principles, you have two options to do that. The first thing is to work with thermosensors, like for instance, the temperature verification system. With a system, you can check the temperature accuracy and homogeneity, and you can also adjust the cycler in case this is needed. Another option is to check the performance by means of PCR amplification. So you could use a commercially available test kit. There are test samples, test plates on the market, but you could also use your established positive control to check if your cycler is performing well. And now I would like to talk about optimization of your PCR protocol. You might have heard about the 1D gradient function. So in case you have a new set of primers, then it makes sense to test the optimal annealing temperature. And this can be done with a 1D gradient. So for instance, here you can try different temperatures between 52 and 72 degrees during the annealing step. And after the PCR, you know the optimal annealing temperature for your primers. In case that you have very complex samples, so for instance, a very long target DNA or a target DNA which is GC rich, then it makes totally sense to also optimize the denaturation temperature. And the master cycler X50 from Eppendorf offers a 2D gradient function. And this means that you could test and optimize two different temperatures in one experiment. So here you can test 12 different annealing temperatures within one run. And here you could test 8 different denaturation temperatures. So in total, you have 96 combination of different temperatures to find the optimal combination for your PCR. And this helps you a lot to save time because you are 8 times faster with your optimization of denaturation and annealing temperature than with a 1D gradient. And I just want to give you one example how the results could look like. So here you have the results of the 2D gradient. So here you have the different annealing temperatures which have been tested and the different denaturation temperatures that have been tested. And what we want to have is a clear, nice band shown here and no second smaller band, which is unspecific signal. And you see here that if you're really looking for a nice yield, so a lot of amplicon, you maybe go for this combination of temperatures. If you're more interested in a very pure product, then maybe this combination of temperatures is suitable for you. If you look for a nice compromise, a good balance, then you can use this combination of temperature. So the 2D gradient helps you a lot to improve your results. So you have higher specificity, means nicer bands for your publication, for instance, and you have cleaner DNA for post-PCR processing. And by improving the yield, you can go for faster protocols if you want and save a lot of time. You can go for lower reaction volumes, and this will save money. You can work with less template if you want, and you have also more template for downstream applications if this is needed, especially if you're working with very difficult assays, then sometimes it makes sense to have a high concentration of DNA for the further steps. And one other topic I would like to address is the noise level of the thermal cyclers. And here at Eppendorf, we have one big lab with a lot of thermal cyclers from different manufacturers. And believe me, in case they are running at the same time, it's very noisy. That's why we asked the German Technical Inspection Association, called TÜV in German, to measure the sound power level of the cyclers you see here. And the sound power level was measured during the idle mode. Idle mode means that no application is running. The sound power level was measured during the PCR run and also during the hold step at 4 degrees. And you see that the mass cycler X40, for instance, emitted a sound power level of up to 40.9 dBA, and this could be compared with a noise you find in a library. So not very noisy. There are other cyclers, they emit sound power levels over 50 dBA. So here you have a noise level, which is in between rainfall and conversation. And imagine you would like to work on experiment and you have to concentrate and someone is sitting next to you and is talking all the time. That would maybe lead to the point that you make mistakes or you have more problems to concentrate, and that it makes sense to use a cycler with a low noise level. And what else, which is important, is if the cycler shows tonality. So if the cycler has tonal noises, and all the cyclers and signals here, which are surrounded by a dashed line, they show tonality. Tonality means that a noise contains a recognizable tone, which is recognizable for the human ear. And this tone stands out from the average background noise. And the presence of such tone is perceived as annoying by most people, saying that the cyclers which show tonality are even more annoying or perceived as more annoying. And believe me, if you run several cyclers at the same time, it can be really, really noisy. Okay, just some additional general tips from my side. So what is important for me is that the manufacturer offers detailed information about the device. So for instance, a comprehensive operating manual. For me, it's important that the manufacturer offers a good service and support. And a plus is also an auto restart function. So an auto restart function is helpful in case that you have a power loss in your lab. So in case of a power loss, you can resume your PCR run after the power is back. So if you're working in a lab where it sometimes happens that the power gets lost, then it makes definitely sense to activate this feature in order to be able to resume your PCR protocol afterwards. And it's nice if the manufacturer provides a solution for program migration. And with this, I would like to show you the literature shortly, which I have used for this webinar. And I would like to thank you for your attention, and I'm happy to answer some questions.
Okay, thanks, Stefan. That was an amazing presentation. I would have certainly found that really helpful going into my PhD. So yeah, we've had quite a few questions from the audience actually. So you touched upon this during the webinar, but maybe you could just summarize and expand on any more points that you're aware of. But what can people do to speed up their PCR?
Yeah, so if you really want to speed up your PCR to the max, then it makes sense to use fast PCR master mixes, as I said, a fast PCR consumable. Then it makes sense to use small sample volumes. And you can think about to use a two-step protocol if this is suitable. And of course, it makes sense to use a very fast thermocycler.
Okay, so you spoke about temperature overshoot. Is there a limit of what's acceptable? That you can overshoot by or undershoot by?
Yeah, so I mean, in case that you see less amplification in your PCR, and you know that the cycler has high overshoots, especially this becomes important during the denaturation step, it could happen that your polymerase is harmed. And what you could do is to test the activity of your polymerase. I mean, this is a bit complicated and takes time, but this is something you can recommend, or I could recommend, or just use another cycler, that uses not so intense overshoots and see if there's any difference.
Okay, thank you. So you mentioned your lab where you've got thermocyclers running all the time. People have asked, what can they do to save energy if they're running thermocyclers every day? Do you have any energy saving tips?
Yeah, so the PCR is energy intensive, of course, and that's why it makes sense to keep the PCR program as short as possible, and especially the hold step is quite energy intensive. So it makes sense to keep this hold step also as short as possible. And we have made the experience that 10 degrees for the whole step is totally sufficient. So 4 degrees are normally recommended, but it's not necessary to use 4 degrees. And some thermocycler models, they have an energy saving mode. And this means that the heated lid is turned off when the temperature of the thermoblock is low. And this also saves some energies. And you can think also of the footprint of the device, also of the footprint of the box in which the device was sent. This is also important. And we are now realizing that more and more manufacturers start to provide the operating manual only in an online format and not as a hard copy. And this also helps a lot to reduce the CO2 footprint.
Sure, that's a really good point actually about not having everything printed out. So you mentioned earlier about small reaction volumes being conducive to fast PCR, but is there a minimum volume that you'd recommend working in?
Yeah, here you have to look into the operating manual of the cycler. So I just could talk about Eppendorf cyclers. We have seen that you could work with 3 microliters. Less really makes no sense. I would recommend to use 5 microliters. But I've seen some cyclers from other manufacturers in which it was stated that you should use 5 microliters. So you really should look into the operating manual.
Okay, thank you. I think we just had a question come in. I'll just have to read this one verbatim. So someone's asked, may I ask if the time of each step in the PCR is critical, and what order would you optimize them in?
Sorry, I didn't get it. Could you repeat it?
So is the time of the question has moved now. So I believe that the question was, what order would you optimize the time of each step in to improve the overall quality of your PCR product? So annealing, denaturation. What would you target first?
Like the first thing I would target is the elongation time, because you find information about how fast your polymerase is, and then you can estimate how long it should be. This is the first thing, and you could check if you're working with a hot start polymerase or not. So hot start polymerases need like 10 minutes of high temperature in order to get activated. If you're working with a polymerase which is not a hot start one, then the initial denaturation step can be shortened to 2 minutes, for instance.
Okay,
So you
thank
don't
you.
need that long initial denaturation time.
Thank you. So someone's asked, what is the rule for the length of the final extension step after your 35 cycles of amplification?
This is also a very good question, and I ask also myself, why do we need this in this final elongation step? And what I have found is that this fine elongation step is just there in order that some sequences are not fully in full length and need to be fulfilled, and that's why we have this final step.
Okay, thank you. That's good to know. I didn't know that myself. So finally, then, are there any disadvantages of fast PCR that you're aware of?
Yeah, the disadvantage is that you cannot use high volumes. So if you need to have a lot of amplicon after your PCR, maybe it's better to use conventional master mixes if time is not that important. And I don't know so much about prices, but I have seen that fast PCR master mixes are slightly more expensive. So if money is also important, then this is also one disadvantage.
Okay, thank you. They keep coming. Sorry, I'll just look here. So how long can you store your amplicon before running the gel? Do you have any advice on that?
So we have seen that it is totally fine when you're just interested in the DNA, which is normally the case after PCR,
Yeah.
that you can store it in the thermocycler over a whole weekend, like at 4 degrees or 10 degrees. But as I said, it's not recommended as this is quite energy intensive, but you can do it without having any problems afterwards.
Okay, thank you. I think that's the end of all the questions that came in. So yeah, thank you again, Stefan. And that brings us to the end of the webinar. So thanks for your time giving the talk and for answering everybody's questions. And yeah, thanks to our sponsor, Eppendorf, and thank you to you, the audience, for taking the time to attend and listen in today. So until next time, good luck with your research from us at Bite Size Bio and at Eppendorf. Thank you.
Thank you. Bye.